All right, we're moving to some chapter 11 stuff. Starting off here in 11.1. I think this whole chapter is going to be a little bit difficult for me to write out in words. So I'm going to be bouncing back and forth between the book and writing stuff out, just because there's a lot of graphs and a lot of pictures for this. In this first section, we're going to be looking at something that you, I hope, have at least seen a little bit before. And that's going to be parameterization stuff. So if you haven't seen it, it's all right. I'm going to kind of start over from the beginning. So what we want to do is we want to describe the path of a particle along a curve. And to do that, we're going to write the x-coordinate of the particle as a function of some variable t. You can think of it like time, but really that's what's going to be our parameter variable. And then we're going to write our y values as a function, a different function of t, g of t. So quick little definition here. If x and y are given as functions, and these are the same two functions up top here, x is given as f of t, y is given of g of t, over some interval I of t values, then the set of points, so these are going to be our normal points for our path x, y, but we're not going to think of them like that. We're going to think of them as f of t, g of t, defined by these equations, is what's called a parametric curve. Okay, and then the equations are parametric equations for the curve. All right, so anytime we're talking about a parametric curve or parametric equations, we are talking about the equations that we define our movement variables x and y to be. If we were in 3 dimensions, then there'd be a third one here as well. So for those of you moving on to Calc 3, we're going to come back to this, but add a third dimension onto it. That variable t that we're talking about, just lowercase t, is called a parameter for the curve. And then that I that we were looking at, that capital I, is what we call the parameter interval. Okay. We're going to start off here with an example. It's kind of difficult to go back and forth between just normal functions y of x and these parametric functions. So I think it's going to be nice here for us to see a couple of examples. The first example we're going to look at is just x is equal to t squared, y is equal to t plus 1, and this is going to be on the interval negative infinity to positive infinity. Okay, we need to know what this graph looks like. Remember, this is going to be the path of a particle moving through space. Our x-coordinate is as a function t squared, our y-coordinate is as the function t plus 1. The easiest way to figure out what this graph is going to be is just by plugging in different points. So let's just try some t values. Let's see if I can get a table going here. Insert a table. That's good enough. So my first column here is going to be the t values, then we'll get the x and the y values from that. So let's just see what happens at t equals 0. If I plug t to be 0 into these two equations, I get x is 0, I'm going to get y is a positive 1. If I plug in maybe t to be 1, I get x is 1, and I get y is 2. If I plug in t to be 2, I get x is 4, I get y is 3. I'll add another column here. Insert rows below. Oh, that was easy. All right. Let's see what happens when we go in the negative direction. If I plug in negative 1 for the t, negative 1 squared is positive 1, and then here, negative 1 plus 1 is going to be 0. These ordered pairs that we're getting are going to be the ordered pairs that we're graphing in our map. So the ordered pair 0, 1, the ordered pair 1, 2, the ordered pair 4, 3, the ordered pair 1, 0. So if we were in class, I'd really map these out one by one, but now I'm going to jump over to the book and we'll just kind of see the finished product. So here, oh, not there, sorry, next page. Here is going to be our finished product For our parametric equations here. So notice that we have all of those points that we had, right? We plugged in 0 here, and then we get the point 0, 1, and then the point 0, 1 is here, the vertex of this parabola. When I plugged in 1, I got the point 1, 2, so that's this point up here. When I plugged in 2, I got 4, 3, that's this point up here. And then if I went in the negative direction, negative 1, remember, gave me 1, 0. So it has all of those points that we had. Now, what's really nice about parametric equations is that you get the graph, of course, but not only do you get the graph, you get the direction that the particle is traveling along that graph. So here my particle is coming up the parabola and then going out to infinity, up and to the right. Okay. If it's difficult for you to graph it out that way by just plugging in points, oops, didn't mean to do that. There is a way to go back and forth between parametric form and then just explicit or implicit form. And to do that, what you want to do is just solve one of your parametric equations for t and then plug it into the other one. So what we can do is that for the second equation here, I could solve that for t and just write that as 1 minus y. Not 1 minus y, sorry, y minus 1. And I'm going to just replace that t into the second equation. So if I substitute that t into the second equation, I get x is equal to y minus 1 all squared. I know it's probably been a while since you've been in an algebra class where you've looked at parabolas in this form, but this is a certain form of parabolas. This says that your vertex is at the point 0, positive 1. If I go back over to my thing, 0, positive 1 is the vertex, and it's a right-facing parabola because we have a positive number value out in front of the thing that is squared. And again, positive-facing parabola. Okay, so that was just one example here. There is something else that we want to look at. So a lot of times, you're not going to be given the parameterization. You're going to be given the function like this, or I guess it doesn't have to be a function, but the equation like this, and you're going to have to translate it over to a parameterization. So how to find a parameterization. One way to do that is to use what's called the natural parameterization. Okay, so any function, this is the definition here, any function y is equal to f of x, and it does have to be a function to do this natural parameterization, can be given a natural parameterization of the following. So what you want to do is you just want to set your x to be equal to the parameter t. And if x is equal to the parameter t, that means that your y is just plugging in f of t. So just a really basic example here. If you were given some function y is equal to x squared minus 4, and you want to write out a parameterization for that, one parameterization for that is just setting your independent variable x equal to the parameter t, and then your y would just be equal to plugging in t into the function, so t squared minus 4. And then you'd want to pick the interval here, and then whatever the interval needs to be. In this case, it would have to be from negative infinity to infinity again to get the full parabola. Okay, there is a way more complicated example here, and I'm going to look at the book to do this example. This is not something I would expect you guys to be able to get done on your own, and just know that that is perfectly okay. There's also these other examples in the book that I would recommend that you look through. It's just that I don't want to make this video too long. We're going to be looking here at example 6? Not example 6. Where's the example that I want? Here we go, cycloids. This is the example that I want to do. So a cycloid is kind of mapped out in situations like this. So hopefully you can just kind of see the picture and see what I'm talking about here with a pendulum that kind of bends as it goes up. But this is another definition of a cycloid, and I thought this problem was really fascinating, so I do want to look at this one. So here's the question. A wheel of radius a rolls along a horizontal straight line. Find parametric equations for the path traced by a point P on the wheel's circumference. The path is called a cycloid. All right, so if we have this wheel that's initially starting at 0 and it has a radius of a, and we just start rolling the wheel, a particle on the edge of that wheel, as it moves forward, is just going to be rotating around. And it makes these pretty cool looking shapes. Let's see if they graph it out a little bit better. Yeah, here we go. So it makes these kind of shapes. This is a cycloid shape that it's making here. Okay, but if we wanted to map this out using parametric equations, it can get a little bit complicated. These are the answers, but I do want to explain why this is the answer here. Let me zoom in some. Okay, if you think about the x-coordinate of the particle on this wheel, it has moved to the right a distance AT. This distance AT represents the center of the circle, right? So you can see that from here. If the radius is A and a time t, we don't want to think of that as the time necessarily. We kind of want to think of that as the angle that has been traveled. But we'll just consider it time for now. So AT has now transpired, and that's the distance that the center of the circle has moved. We're going to add on to that my radius A times cosine of the angle theta, where cosine of theta represents this angle that comes from the right triangle here, where cosine is the horizontal distance, remember. So if my particle is to the right of the center, this is going to come out to be a positive value for that little tiny extra distance here. If my particle is on the left hand of my circle, then this is going to come out to be negative, and it's going to subtract away from that AT distance to just give me this distance from wherever the particle is to the y-axis. Okay, so that's the x. Y is very similar. My y value, I only have the radius A. That's the distance from 0 up to the center of the circle, and then A sine theta, and that's going to be very similar. So if my particle is here, then if it's above the center, it's going to come out to be a positive value that adds onto that radius A to get this tiny little distance here. But if my particle is below the center, then A sine theta is going to be negative, and it's going to come down. Okay, so this would be the parameterization. The only problem is that we have two different variables in the parameterization, t and theta. So this next little part is just solving theta to be in terms of t. So to express theta in terms of t, we observe that t plus theta has to equal to 3 pi over 2. And that's just in this picture right here. Right? If I take t and then I add on to that theta, I have a 270 degree angle, and 270 degrees is this 3 pi over 2. So just plugging that in and solving for it, we end up with these as our final answer here for the parameterization. Again, I would say that this question is way too complicated to ask you guys to do on your own. I just want to show you an example of how parameterizations can take something very, very, very complicated and map it out into kind of nice little function values for the x, the horizontal distance the particle has traveled, y, the vertical distance of the particle.